All right, let's dive right into this explainer. Welcome to the flight deck. Today we're talking about advanced aerial combat tactics, but, well, instead of fighter jets, we're applying these high-level strategies to tackle the absolute toughest math questions Cambridge can possibly throw at you in your O580 calculations. I want you to picture two very different students taking this exam. First, we've got Alex. Now, Alex is a classic case of cognitive overload. When confronted with a massive, complex calculations question, Alex just panics and dumps every single formula they can remember right onto the paper. No analysis, no strategy, just hoping something sticks. And guess what? The examiner's red pen just circles the whole mess. Then, on the other side of the room, we have Sam. Sam is fast. Actually, way too fast. Sam just rushes through the paper, completely misses the crucial command words and constraints, and just punches strings of numbers blindly into their scientific calculator, just hoping for the best. Look, both of these students are essentially crashing before they even reach cruising altitude. But today, we're going to change that. We are giving you a bulletproof, systematic strategy to tackle this paper. So here is our flight plan for today. We're covering 4 critical phases. We kick off with Phase 1, the rules of engagement. Then we move into Phase 2, target acquisition. Next is Phase 3, the flight sequence, and we'll wrap things up with Phase 4, evasive maneuvers. Before we continue, subscribe to our YouTube channel, Ace the Exams, at AceTheExams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's strap in and get started.
Let's move right into our first section, Phase 1, Rules of Engagement. We're starting by decoding inequality symbols. In Cambridge Mathematics, your mathematical symbols are your absolute, non-negotiable parameters. Think of it this way. If you misread the symbol, you fly totally out of bounds. These specific symbols dictate exactly which numbers are allowed to be in your final answer. It's basically your radar lock. Now, an equal sign, that means you have one very specific target. Boom, done. But inequality symbols, like greater than, less than, or not equal to, mean you are looking at a designated zone of acceptable targets. For example, if the exam paper says x is greater than or equal to 3, your acceptable flight path includes 3, 4, 4.2, 5, and so on, all the way out into infinity. Because of that or equal to line, 3 is a perfectly valid target. But if it simply says x is greater than 3 without that little line underneath, the number 3 is strictly off limits. If you include it, that's an instant crash.
Now, you might be wondering, what happens when things get flipped around? Well, it's actually fascinating how you can mathematically flip an equation to gain a totally different perspective. 5 being greater than x is tactically exactly the same thing as x being less than 5. See, examiners love to write inequalities backwards, just to test if you're actually reading the parameters, or if you're just skimming for numbers. 5 is greater than x might look a bit intimidating at first glance, but if you just pivot your perspective, it simply means x has to be less than 5. That's it. Your acceptable integer values are just 4, 3, 2, 1, and so on. It works with negative numbers too. -7 is less than or equal to x is exactly the same as saying x is greater than or equal to -7. You've really got to be able to view the target from multiple angles without losing your lock.
What's really cool is how we can translate real-world scenarios directly into these tactical mathematical parameters. Often, the evidence you need in a word problem is totally buried in English, and your mission is to translate it into math. Take a football pitch, right? The maximum number of players from one team allowed on the pitch is 11. So let's let n be the number of players. Because it's a maximum, n cannot exceed 11, but it can be exactly 11. Therefore, n is less than or equal to 11. Pretty straightforward. But what if the examiner throws a curveball and adds a minimum of 7 players? Suddenly, your target is boxed in. You write this as a compound inequality. 7 is less than or equal to n, which is less than or equal to 11. You've just created a perfectly defined corridor of acceptable values. Same goes for a stadium. Maximum stadium capacity of 20,000. Boom, x is less than or equal to 20,000. You're establishing the exact perimeter.
When it comes to plotting these on a number line, your visuals are absolutely everything. It's like plotting your flight path on a physical map. If the line says x is less than 5, you have to draw an open circle above the 5 and point the arrow to the left, descending through 4, 3, 2. That open circle, it's a massive visual warning sign, literally shouting, do not land on 5. 5 is not included. But if the inequality is x is greater than or equal to -7, you draw a solid, filled-in circle over the -7 and draw your arrow to the right. That filled circle is your green light. It means -7 is a designated safe landing zone. Trust me, drawing an open circle when it should be filled is an immediate, unnecessary loss of altitude on your exam.
All right, moving right along to phase 2, target acquisition. This is all about how to handle sorting mixed magnitudes. So what happens when the exam throws a complete mess of mixed units at you? Well, trying to compare them in their raw, given format is going to result in immediate cognitive overload. To effectively sort a chaotic list of lengths, you absolutely must follow a strict, systematic normalization strategy. Step 1, identify the mixed metrics. Step 2, normalize them all into a single unit, like centimeters. And step 3, only then do you establish your final order. Imagine you're given 2 meters, 60 centimeters, 800 millimeters, 180 centimeters, and 0.75 meters. The prompt asks for the orders starting with the smallest. If you just scan the raw numbers, you're going to fail for sure. Let's normalize. Convert everything to centimeters. 2 meters becomes 200, 60 stays 60, 800 millimeters becomes 80 centimeters, 180 stays 180, and 0.75 meters becomes 75 centimeters. Wow, suddenly your radar screen is perfectly clear. Order from smallest, 60 centimeters, then 0.75 meters, and always write your final answer using the original format from the question, then 800 millimeters, 180 centimeters, and finally 2 meters. See? Systematically executed.
You are going to need to apply this normalization strategy across the board. It doesn't matter if you're sorting tricky decimals, evaluating fractions, converting masses, or unifying volumes. Think about a mass question: 4 kilograms, 3,500 grams, 3/4 of a kilogram, 700 grams, and 1 kilogram. The prompt says starting with the largest. Naturally, your brain wants to just look at the number 3,500 and assume it's the biggest, right? It's a trap. Normalize everything to grams first. 4 kilograms is 4,000 grams. 3,500 stays exactly the same. 3/4 of a kilo is 750 grams. 700 stays the same. 1 kilo is 1,000 grams. Now the correct order from largest is glaringly obvious. 4 kilo, 3,500 g, 1 kilo, 3/4 of a kilo, and finally 700 g. Normalization is literally the only way to clear the fog of war. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, welcome back. Let's launch into phase 3, the flight sequence. This is a zone where so many students needlessly lose marks simply by reading math from left to right, instead of following the true structural hierarchy. Without this universal protocol, math would literally be chaos. I want you to think of it exactly like air traffic control. You have multiple planes, addition, subtraction, multiplication, division, and they are all trying to land on the exact same runway. If they approach in whatever random order they feel like, you have a disaster on your hands. The mathematical convention, the order of operations, assigns strict priority levels so that every single calculation is executed with absolute precision. This ensures everyone, everywhere, arrives at the exact same numeric destination. This right here is your non-negotiable hierarchy. Number 1, you must clear brackets first. Number 2, power through your indices second. Number 3, handle multiplication and division. And finally, execute any addition or subtraction. Let's see this actually play out. Take the simple problem 8 times 3 plus 2. If you just casually read left to right, you might say, well, 8 times 3 is 24, plus 2 is 26. Now here, reading left to right happens to work, but purely because multiplication inherently outranks addition anyway. But what about 4 plus 6 times 2? If you just blindly go left to right, 4 plus 6 is 10, times 2 is 20, and boom, that is a crash. Multiplication has priority. The 6 times 2 plane lands first. That's 12. Then addition clears the runway. 4 plus 12 is 16. Priority dictates reality. Take a second and really look at this calculation. Ask yourself, how on earth can the exact same numbers and operations yield 2 completely different results? Look closely at these 2 strings. In the first calculation, we have -4 times, open bracket, 8 plus -3, close bracket. Brackets hold supreme authority here. We absolutely must evaluate inside that bracket first. 8 plus -3 is 5. Now we have -4 times 5, which gives us -20. Easy. But in the second calculation, there are no brackets at all, so multiplication takes priority over addition. We calculate -4 times 8 first, which is -32. Then we add the -3. Landing is way off at -35. -20 versus -35. The numbers are identical, but the structural sequence changes literally everything. And that brings us to our final leg, Phase 4, Evasive Maneuvers. This is where we learn to dodge the biggest trap in the exam hall, blindly trusting your own calculator. Look, your scientific calculator is an incredibly high-performance machine, but it is entirely, ruthlessly literal. If you input bad intelligence, it is going to give you a mathematically perfect, yet totally incorrect answer. If you physically type 2 plus 3 times 4 directly into a calculator, it performs 3 times 4 to get 12, then adds 2 to output 14. But what if the question was actually asking you to find the total of 2 and 3 and then multiply that bundle by 4? By simply placing brackets around the 2 plus 3, you forcefully rewrite the rules of engagement. You are actively commanding the calculator, stop, execute this addition first. 2 plus 3 becomes 5, times 4 is 20. Always remember, you are the pilot. The calculator is just the autopilot. Your scientific calculator is only as smart as the brackets you feed it, period. As the official course examiner protocol strictly states, it is important to use brackets when dealing with more complex calculations. Guys, this isn't a friendly suggestion, it's a survival tactic. When you're confronted with massive fraction equations on the exam paper, typing the whole thing out in one long continuous string causes the calculator to rigidly apply the order of operations, dividing the wrong numbers at exactly the wrong time. Think of brackets as physical blast shields. They protect different parts of your calculation from interfering with each other prematurely.
Let me show you exactly what I mean. For a complex fraction like 12 plus 9 over 10 minus 3, if you literally type 12 plus 9 divided by 10 minus 3, the machine will do 9 divided by 10 first, outputting something like 11.9. Total disaster. The correct tactical input is open bracket, 12 plus 9, close bracket, divided by, open bracket, 10 minus 3, close bracket. This forces the calculator to resolve the entire numerator to 21, the entire denominator to 7, and only then divide 21 by 7 to get your perfect answer of 3. Same exact thing with the second example. Open bracket, 20 plus 12, close bracket, divided by 4 squared. Protect your numerator before you even think about dividing by the denominator.
Seriously, look at just how insanely powerful brackets actually are. Let's run a quick simulation on the base sequence. 12 divided by 4 minus 2 plus 6. If we calculate it totally raw, respecting the normal order, 12 divided by 4 is 3, 3 minus 2 is 1, 1 plus 6 is 7. Okay. But bracket the 4 minus 2, and suddenly you have 12 divided by 2, which is 6. 6 plus 6 is 12. Bracket the 2 plus 6 instead, well, that's 8. 12 divided by 4 is 3. 3 minus 8 is negative 5. Put massive brackets around everything after the division sign, so 4 minus 2 plus 6 is 8. 12 divided by 8 is 1.5. Same numbers, same order. Just by moving those tiny little brackets, your entire flight path changes completely. As we wrap up this explainer, we really have to look beyond just the numbers on the page. We live in an age where technology is incredibly powerful, and man, it is so easy to just hand over our thinking to a scientific calculator, completely expecting it to do all the heavy lifting. But as we've clearly seen today, the machine doesn't understand context. It doesn't understand your intent. It only understands the strict, unyielding logic that you program into it. So you have to ask yourself, in your exams, and honestly in life, are you letting the tools dictate your direction, or are you the one firmly in the pilot seat, mastering the underlying logic to command exactly where you want to go? Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to Ace the Exams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Keep your altitude high, and I will see you in the next explainer.